Now, the problem is that all of that is bullshit because if this is not the truth, that those three assumptions are not satisfied, which they never are, then the confidence intervals we get are bad. Okay, so let's recall that these assumptions are that the means of the conditional means of the outcome given these covariates vary linearly. We also assumed that the distribution of the outcome, the conditional distribution of the outcome within each of these strata is this normal distribution. And we also assume that the width of that normal distribution does not change from stratum to stratum in the population. All of those are very untenable. In general, there's no reason why the situation should not look like this. Okay, so here's the setup where in different strata of the population, you have conditional means that are varying in a nonlinear way. So let's say if this is like age, right? Young people might have a high risk for something, and then in middle age it goes down, and then as you get older, you have higher risk again, right? There's also no reason why the distribution of y given in a particular stratum should be a normal distribution. So here, for example, in this stratum, the distribution seems to be kind of right skewed. In this stratum, it has two modes. It's not even unimodal. And moreover, there's no reason that the width of those distributions should be the same, that the variance of y given x should be the same from stratum to stratum. So here, for example, in this stratum, we have a very tightly clustered outcome, right? If you're in this stratum, we know pretty sure that your outcome is going to be around this mean mu5. But for people who are in this stratum, there's a lot more variability in the outcomes. And all of this is perfectly natural. There's no reason why this shouldn't happen, right? And so the problem with the classical standard error in those assumptions, if you remember this picture where we have some kind of true value of the thing we're trying to estimate, we come up with an estimator that is maybe unbiased for that and is asymptotically normal. Then we come up with some formula that describes what the variability of that estimator is based on some population parameters. And then we have to estimate what that number is. Well, the estimate for the classical standard error, we just did a plugin, so that's pretty much fine. The problem is here, right? The problem is that formula that we derived is contingent on those assumptions being true. And so when those assumptions are not true, this is not the true standard error. The number that we can calculate has nothing to do with the actual sampling variability of beta hat. So we can see that here. Let's play around with this. So I have data being generated. X is a uniform random variable. Now y is x plus some random normal random noise. So we have two out of three of the assumptions are being satisfied here. One, the conditional mean actually is linear, right? So y is x, so it's 1 times x plus some mean 0 noise. And the other one that's satisfied is that this noise distribution actually is normal. So the only thing that is not satisfied is that the standard deviation of that normal distribution is changing with x. So here I have x being used to define the standard deviation. So it basically looks like this picture. The only difference is that we have distributions of different widths at each x. So it looks like this. So around 0.5, we have very tight conditional distribution of y given x. And then for values of x more on the fringes, we have more spread out outcomes. Okay. So let's say, so obviously in this case, there is like a true coefficient. That's very clear. It's 1, because it's y equals 1 times x. So this is and the intercept is 0. So here, this is the kind of true regression line we would like to get. We can run linear regression. You're going to see with n equals 200, you're actually going to get a decent enough fit. But if you can run your confidence interval code on that as well. So confident m, and then get out the one for x. And now you want to check if the confidence interval actually contains this true coefficient, which we know is 1. Okay? And we're going to repeat this whole thing many, many, many times to see how often does the confidence interval actually contain this 95% confidence interval. How often does that actually contain the true value of the coefficient? And if you do this, you calculate the coverage, the number you get is actually like 0.88, all right? That is not close to 95%. So we are undercovering on the confidence interval, and you get similarly with p-values, you're going to get p-values that are smaller than they actually should be, and that means more false positives. So you're more certain, in this example, you tend to be more, if you're using this classical standard error to get your confidence intervals, your confidence intervals are actually going to be narrower than they need to be to reflect the true sampling variability in that coefficient. And that is not good, okay? And some people will tell you, oh, what you have to do before you do anything, you just have to test that these assumptions are true, okay? Just test that there actually is linearity, that the noise is normal, the noise is homoscedastic, whatever. And I mean, I would say, one, most people don't know how to do that. And two, if you're going to do that, you actually need to use a separate data set. So and we'll talk more about that, I think, in the next lecture. But there's no reason to have to. That's what we're going to talk about in the next section, that there's a different formula, basically, for the standard error that just takes all this into account. So there's no reason, there's no need for this, okay? And this is a general point. Again, we'll return to this in the next lecture, but testing for assumptions is not great practice, and it's something that a lot of people tell you to do. But it actually kills your confidence intervals if you test and then you do something based on the result of that test. And also, most people just kind of test, and then no matter the answer, they say, oh, it looks normal enough, it's close enough, and they do the thing based on the normal approximation anyways. The normal assumptions anyways. And so most people don't even act on that. So again, we'll talk more about that later, but this is just generally not a good thing to do. Okay, so what's the alternative? Just use this robust standard error. It's really easy. So what are we going to assume here? Absolutely nothing, okay? The vaguest of regularity conditions. And now you have to do some math, and that math is harder. But you know what? Why should you care how hard this math is? You're not the one doing it. Somebody else already did it. Okay. The point is that at the end of the day, you just get a different formula for what this variance of the coefficients is. And the formula looks like this. And you'll see it has this beta star in it. And beta star reflects essentially the population regression coefficient. So remember, what do we mean by true coefficient? There is no true coefficient, right? Like, let's say here, let's say these are our population data. This is a population data set, not a sample, population data set. And here you can clearly see that the conditional mean is nonlinear. It's this black line. However, if you were to run linear regression, the line you would get is this. So whatever the slope of this line, that's what we mean by the kind of true coefficient. It's kind of like it's the best linear approximation in the population data to this conditional mean function. So that's what this beta star is, and this is the equation that you get. Again, it doesn't matter. You don't have to memorize this. You're never gonna have to use this. I'm just showing you so that you understand that it is different, right? It's different than the other thing that we saw. And a plug-in estimator, you just, instead of expectations here, you put in these sample averages, and besides that, it's all the same. So how do you calculate this in R? You don't have to implement that. You can just use vcov, but now instead of vcov, you use vcov HC. That's it. That's the only difference. It's just as easy, okay? vcov HC. And if you want to check that indeed this gives you the same thing as if you had actually tried to implement this plugin estimator here, you can do that. I've given you the code to show you how to do it by hand here if you want. So you'll see that if whatever you run with vcov HC is actually going to be a bit different than what you get with vcov. So we can go here, and if you look at vcov M, and then vcov HC. Sorry, you need to load this package called Sandwich. You need to install that package. Okay. All right. So let's see. You see they're quite similar. Okay, they're quite similar. This is vcov HC. This is vcov. Sometimes the vcov HC numbers are smaller. Sometimes they're bigger. So here, for example, you see This number is a little bit bigger than this. This number is quite a bit bigger than this. And so the inference that you get is going to be different. But the confidence intervals that you're going to get from this actually reflect the actual sampling variability without having made these assumptions. So I think maybe I have so here, you can compare it. It's just as easy. The only thing that you change is vcov HC versus vcov, and you have to use this standard package. And you can build an estimated confidence interval. So let's see again what that looks like. This is, okay, so now this is the confidence interval. So you can see it's a bit wider than the one that we had before. So here the upper bound was 24.7, and now we're at 25.1. So we're just a little less certain about what that coefficient is. And that's often what will happen when you use the robust standard error, is that your confidence intervals will be a little bit bigger, something like this. Not always. Sometimes it'll actually help you. Sometimes the confidence you'll have more confidence than you had before, but often they'll be a little bit bigger, and that kind of is reflective of the fact that there's more uncertainty due to the fact that you actually do not know the form of the model, right? You don't know that it's linear. You don't know that the errors are homoscedastic, and so you have to take that uncertainty into account effectively, and that's what this robust standard error is doing. So you can do it like this manually. You can also use, if you want to get a kind of regression table like this that matches what you get if you do summary of M or like confint, that kind of stuff. You can do it like this. So you have to use this library, JTools. There's other things too. This is something I just found the other day. And it has this function sum. And you just put your model here. So it works just like summary. Robust, you have to say robust equals HC3. I think this is discussed in the challenge assignment. You could also put HC1 here. You'll see the numbers are pretty much the same. So this just tells it, use the robust standard error. Don't use the classical thing. And then say, yeah, give me a confidence interval as well. And you can even say, I want it 90% or 95%, whatever you want. If you just say true, it's going to give you 95%. And you get this nice table here, which looks a lot like what you get when you just do summary of M. But this uses the robust standard error instead of the standard classical. Okay, so just to convince you that this actually works, this is the exact same simulation that I did with the classical standard error, where I saw the coverage of the confidence intervals was like 88%. Now, the only thing I changed is in the calculation of my confidence interval, I changed from vcov to vcov HC. And now when I calculate the coverage, it's 95%. Actually, a little better than 95%. So the problem, again, with the classical standard error estimator is that it's biased, right? That formula does not actually reflect the true classical standard error, the true standard error of the sampling distribution of the coefficients is something else. So it's not biased when those assumptions are correct. So here's an example where this is like, again, think of this as like my population data set here. And so here you see at each stratum, yeah, the errors are roughly normal. Everything is nice and linear. And those normal errors the width of those normal errors don't vary with X. And if you look at the sampling distribution of the estimated standard error of the coefficients, and here this is the true standard error of the coefficients. And this is the case where my data generating process is different. And here, one of those assumptions is violated, which is that now we have heteroscedastic instead of homoscedastic noise. And you can see that the classical standard error is smaller in this case. The estimate of that classical standard error is smaller than the true standard error of the coefficients. So this is just trying to hammer it one more time. Recommendation here, always use the robust standard error. It's just as easy. It works kind of without assumptions. And it's recommended. It's not just me telling you this. This is the FDA, okay? Because the FDA knows that people out there in the world are just doing summary M, and that in many cases those confidence intervals can be too small, and sometimes they're bigger than they need to be, but they're just wrong. There's no reason to do this. And so the FDA is basically saying, please, for the love of God, use the Huber-White Huber-White or robust or sandwich estimator. These are all just different terms for the same thing. Or just bootstrap. If you don't want to think about it, you don't want to worry about these different formulas, just bootstrap, okay? Rather than the nominal standard errors, which can be inaccurate if the model is incorrectly specified. So like you didn't put an interaction term. Boom. If there really was one, and now you didn't include it, too bad. Your standard errors are going to be bad. And these are often the default methods for estimating standard errors in most statistical software packages. So there's just no reason for people to be doing this. There's no reason for people to be teaching the classical standard error really anymore. I have to show you just so you know what not to do. But this is the robust standard error has been around for 30, 40 years, and we're still doing this. So that's just where we're at. Okay, so let's hammer this home. Set up this data generating process, and let's consider regressing y on x. There's no true coefficient in this case because we have x squared, but we can still see if the estimated standard errors reflect the true sampling distribution. So let's see. Let's do 2. All right. Yeah. Okay. So this is our data generating process. We can sample some data as always. Do the classical standard errors reflect the sampling distribution of coefficients? So let's basically do the experiment a bunch of times and see what happens. Okay, so what I have to do is generate some data. N equals what? I didn't tell you what n is. Let's say n is 200, okay? So generate some data, run the linear model, and now I need to get the standard error. So okay, so this is generating my classical variance covariance matrix estimate, getting the diagonal of that, and taking the element corresponding to the x, because there's going to be intercept on x, and then taking the square root of that. That gives me the estimated standard error. So okay, great. So and let me also record the coefficient. So the estimated coefficient is this. All right, and let's put that into estimates. I don't know if I've showed you this before. It's totally cursed, but you can assign that way in R as well as that way. Okay, so now we have estimates. You can see here is the, oh, I did this wrong. Hold on. So I want to put this in a little data frame or a list, either way. So each time I run the experiment, I'm going to get a coefficient and the estimated standard error. Coefficient, estimated standard error, and I plop that all into this data frame. So it looks like this. So this data frame has 10,000 rows because I reran the experiment 10,000 times. Each row is the coefficient I got on x, and then my guess of that variability of that coefficient. So both of these things vary, right? This is a guess. This is a guess. Now what I want to know is, on average, is this guess actually reflective of the variability of this guess? Okay, so what I can do, let's calculate what is the variability of this guess, right? That is the, I can just ask about the standard deviation of the estimated coefficient, right? What? Oh, sorry. I meant summarize, not summary. Okay, so this is the actual sampling. This is the true standard error, basically, the actual sampling standard deviation of my estimated coefficient. Now, what I want to know is this guess any good? And already just by looking at it, I can tell you it's not that great, right? Because the number I should be getting is about 0.09, but in all of these, I'm getting less than that, 0.08, 0.08, 0.07, so on and so forth. The typical way that I like to do this, that you'll see in other simulation studies, is you will take the, so let's call this true standard error, and then you'll compare that to, for example, the mean of the estimated standard errors. So by comparing these, you're basically asking, is my standard error estimator biased or not? Because this is the true standard error that you should be getting, and then this is the mean of those. So just comparing these, this gives you the bias, right? Forgot a comma. And yeah, you can see that there's a pretty substantial bias here. So next part of the question is, what about the robust standard error? So we already have this simulation set up. All we need to add here is this. Okay. So the estimated coefficient is the same either way. The only thing that's changing is the way that we're estimating the standard error. Don't know what that's about. Just ignore it. Okay, so here we have true standard error. The mean of the estimate for the classical estimate and the mean with the robust. Obviously, this is very close to that, whereas this is pretty far off. So robust standard error wins again. Surprise? Not really. Okay, can you explain the result? Why is it that the classical standard error is bad here, right? For that, you have to look at the data generating process and think about what is violated. What are the assumptions of that classical standard error that are not satisfied for this data generating process? And here you see that y is normal, conditional on x, so that one is good. It's actually also homoscedastic. The standard deviation is a constant. It doesn't vary with x. But what is changing is that the conditional mean is actually not linear. So we have an x squared. So you could say, hey, well, if I had just put x squared here, then everything would have been fine, right? Because now, and I will show you actually. Oh, this actually, I'm not sure if this will work because now my, let me see. Is that giving me the right thing? What does this look like? Oh, I think I need to do it like this. Okay, so this is the coefficient on x squared. So here I'm running a regression on x plus some x squared term, and I'm looking at the coefficient on x, which in this case should be about 0 on average. And I'm estimating the standard error both ways. So I think here it should actually be about right no matter which way we do it. Yeah, so that's what you see, right? So now the true standard error matches both of them. So it's still not, I added a nonlinearity, but I also added in my regression specification, I added basically a mutate. So I have x, I have two columns, right? I have the x column and then I have an x squared column, and I'm regressing y onto both of those together. So the relationship between y and both of those things is linear, even though the relationship between y and x by itself is nonlinear if I include the x squared. And I have a linear relationship because I can write y is equal to 0 times x plus 1 times this x squared variable. And we're good. So now it's satisfied. So this is an example of model misspecification. So I have this x squared term, but I omitted it. And because of that, now my classical standard error is wrong, where it was correct before. But again, there's no need to get into any of that. Just use the robust standard error. You'll always be fine. Okay? Why make it complicated?